What is a turbocharger? A turbocharger is an air pump which supplies air for the engine combustion process at higher pressure and density than ambient air. The turbocharger air contains a higher concentration of oxygen, allowing greatly improved combustion for more power, cleaner emissions, improved engine torque output, and reduces the pumping losses within the engine, offering all-around better performance. The turbo can be separated into two distinct sections: the turbine stage, which is the hot end, and the compressor stage, which is the cold end. The turbine is driven by the waste exhaust gas from the engine, and that in turn drives the compressor, which draws in ambient air and compresses it. The exhaust gas is collected by the exhaust manifold and directed into the turbine inlet. Here, it passes through a nozzle, which is a tube of reducing section, to accelerate the gas to even higher velocity. This size of the turbine inlet nozzle is one of the biggest influences on the performance of the turbine and is referred to by a ratio called A/R. This will be explained in more detail in a later training course. After that, the gas passes into the volute, which is shaped like a snail shell with a reducing section, where it is again accelerated to higher velocity. Finally, the gas passes through another nozzle area, around the turbine wheel inlet or inducer blades. Now the gas is traveling at its maximum velocity, and as the gas enters the turbine wheel and passes between all the turbine blades, it is expanding and releasing energy and causes the turbine wheel to spin at high speed. As the exhaust gas completes its journey through the turbine and exits from the housing, it is now at lower pressure, and it is this pressure difference between the inlet and the outlet which is the key to the turbocharger's performance. The exhaust gas, now traveling at lower velocity, at lower temperature and pressure, continues its journey through the rest of the vehicle's exhaust system, which is also important to the correct functioning of the turbine, as we will see in later training levels. On the other end of the turbine shaft, spinning at the same high speed, is the compressor wheel. For the engine to burn fuel more efficiently, it needs as much oxygen as possible. Compressing the air increases the density, so more oxygen per unit of volume. The spinning compressor wheel draws ambient air through the air filter, which is critical to the correct operation of the turbo, into the compressor inlet, where the air meets the compressor inducer or inlet blades. The air passes between the blades and is accelerated up to extremely high speed. When working at high speed and load, the air passing through the compressor reaches a velocity close to supersonic. So now the air contains a lot of kinetic energy, which is energy due to motion. The next stage is where the compressor converts the energy from kinetic into pressure energy by slowing it down. As the air passes out from the compressor wheel exducer or outlet blades, it passes through an area between the compressor housing and the backplate called the diffuser, which increases in area and allows the high-speed air to expand and slow down, and this creates a high-pressure zone. The air exits the diffuser and continues its journey through the volute, which is again shaped like a snail shell with an increasing section towards the compressor outlet. This continues to allow the air to expand and slow down, ensuring that when the air reaches the compressor outlet, it has reached maximum pressure and density. The turbocharger runs at extremely high speeds for maximum efficiency. Our very largest turbo spins at up to 63,000 RPM, and the smallest rotate at more than 300,000 RPM. If we consider one point on the circumference of the wheel when operating at full speed, that point is traveling at over 1900 kilometers per hour. This high speed of operation is why it is so important that the air is properly filtered before it enters the compressor, to avoid the possibility of foreign objects entering and causing catastrophic damage. The turbocharger is also designed to operate at extremely high temperatures. Modern diesel engines operate with exhaust gas temperatures as high as 860 degrees centigrade, while gasoline engines as high as 1050 degrees centigrade. Just a few centimeters away is the compressor, which may have ambient air inlet temperatures of -30 up to +45 degrees centigrade. This huge temperature difference between the compressor and the turbine is one reason why our turbochargers are designed and manufactured with extremely high precision and must be installed with care and attention. The turbo is ideally situated as close as possible to the source of the energy, the exhaust manifold, but this depends on the design of the engine and vehicle. As soon as the engine starts to run, the exhaust gas spins the turbine and exits through the exhaust system. The ambient filtered air is drawn into the compressor, accelerated to high speed, then slowed down to create high-density air for the engine, called charge air. However, just like any other type of air pump, some of the work done in creating high pressure also creates heat. Hot air is less dense than cold air, so after the charge air leaves the compressor, it normally passes through a charge air cooler or intercooler. The hot charge air from the compressor passes through the many hollow tubes in the core of the intercooler. Ambient air from outside the moving vehicle passes across the outside surface of these tubes and cools them to increase the density of the charge air before it enters the engine. The charge air cooler often contains many hundreds of folded metal fins, which offers a large surface area, increasing heat rejection and the efficiency of the cooling process.